So just of course, I don't know if this was said before, but in general, if the question asks for an answer, it's not just enough to say the answer is 25. You have to show your derivations and your work. Otherwise, you don't get anywhere. Not just statements of an answer, just the whole thing. I need that standard model academia, so that should be clear. If you need an extension for illness reasons, normally I'm happy to grant them, but again, you need to just follow the procedures which are outlined in the intro program, which is that you must get a medical certificate. If you don't get a medical certificate, there will be no extension granted. So these can be done retrospectively. So if you were ill and you haven't had a chance to get a medical certificate, you can claim one before the deadline. And you can get a medical certificate, but we'll check. So if you didn't manage to get a medical certificate, then we'll retrospectively cancel the extension.
Did the enrollment code to submit on Moodle? Do we submit on the Moodle page? What is the enrollment code?
I don't remember. I mean, you're already using it.
UCL GM 2012 or GM?
GM 12 UCL.
Some combination.
I did work.
Oh, okay.
Same.
Okay, so everything clear? For those of you who are going to get an extension, you'll need to email me your solution rather than on the Moodle site. The Moodle site will close at midday tomorrow. Not possible to submit after the deadline. Okay, everything clear? Good, so we are going to move on to another topic, which is the junction tree algorithm. So by now you should have some idea about how to do modeling with belief networks. We talked a little bit about Markov networks. You should have some good idea about how to do inference, some forms of inference in singly connected structures. This is based upon the idea of using message passing or dynamic programming, whatever you prefer to call it. It's all the same kind of idea. Now, we also discussed briefly at some point what to do in the case that the graph is multiply connected. So one approach was to go through the graph cutting idea. So where you basically identify a set of variables which would render, when you condition upon them, render the graph singly connected. And then you have to do an exponential number of singly connected inferences where that exponential number comes from the size of the condition. Okay, so the question is there a more general purpose algorithm which we can employ for doing inference in multiple connected structures? And there is, and it's called the junction tree algorithm, and it's one of this whole set of algorithms. So, what is it? Well, the junction tree algorithm enables us to deal with marginal inference in multiple connected structures. We can do both belief and Markov networks. When I say, by the way, marginal inference, I really mean any kind of inference for which this ring structure holds, like we talked about last time. I said that basically this dynamic programming smashing algorithm works not just for max product or sum product algorithm, but actually any algebraic structure within that ring community. And this is the same idea here. We're only going to really exploit those properties as well. So when I say marginal inference. So what's important to bear in mind, and maybe not sufficiently emphasized at some points, is that actually the junction tree algorithm is an upper bound on the complexity of inference. So it's not that when we use this algorithm, yes, we can in principle solve everything, but there may still exist smarter algorithms than this one for a specific problem. Okay, so in some sense it's kind of nice, but it's also a little bit bad in the sense that it's kind of very general purpose. It's not necessarily, we're kind of doing dumb things when we do this. We don't necessarily exploit the full algebraic structure which may be present in the distribution or the object. So it's a little bit a little bit of a sort of unwieldy beast in that sense. Okay, so that's something that you just want to bear in mind. So I'll come back to this point later. Alright, so now the bad news is that we're going to introduce some more graph concepts. Hopefully you kind of got familiar with the idea of leaf networks and markup networks, but there's a couple more graphs we need this junction tree. So one of them is the clique graph. So what is it? Well, we're going to have, like in a markup network, we're going to have clique potentials, so phi. This sort of script x just means a set of variables. So it would be a potential, say potential number 1, on a subset of variables, say x1, and through to, say, the nth clique potential. And what we want to do is, like in a markup network a little bit, we have something like a product of clique potentials. But what's going to happen in addition is we're going to divide by a product of what we call separator potentials. Okay, so we're going to have some other set of potentials, or there are two sets of potentials. So the graph, the clique graph, looks like this. This is a small clique graph. What we've got now is this is representing a set of variables. And this is representing another set of variables. And what's in here is the intersection of these two sets of variables. Okay, and this, what does it mean? This means that you take a product of some function on this set of variables, another product, another function on that, and you divide by the function on the separator intersection of these two sets. That's the representation, what this means in terms of distributions. Quantity. This is not necessarily a distribution. It usually will be, but okay. So this is a little bit tricky because we're going to see lots of similar looking things now. This looks like a factor graph because there's nodes and there's squares. It's not a factor graph, unfortunately. It looks a bit like a markup network because there's node, there's these kind of things, variables, but it's not a markup network because these things are sets of variables. In a markup network, we only have one variable per node. The same variable here, it might appear in different nodes. So we might have, for example, I could represent, say, x1 and x2 might be in the first clique. I might have x2 and x3 in the second clique. So their intersection is x2. That would be an example of a clique graph. Okay. So this would represent phi of x1, x2, some other clique of phi of x2, x3, divided by some potential of x2. So how could we represent this as a markup network? Well, that might be something like x1, x2, x3. Then you'd have a clique, x1, x2, x2, x3, and there might have been, maybe you could have absorbed this into one of these two. Okay, so it's a little bit different.
Excuse me.
Yeah.
The function phi at the bottom, is it the same that the function at the top, the same phi?
Yes. Yeah. So this let's say that we had maybe it's easy to start with something like this. So let's say you had a markup network.
Okay.
So in the markup network, what you have are functions on the cliques of the markup. So in this case, they're just two cliques, so we don't know. This kind of, might I say, some function 5x1, x2, 5x2, x3. That would be sort of a markup. Now similarly though, we could represent this markup network in this way for suitably defined of these. So by the way, I should really write indices on these. Now this is number 1, this is number 2, number 3, something like So in this case, now I could set phi of 3 to be unity.
Okay.
That would then represent this. But just to stop me having to write lots of things all the time, I typically don't put these indices in here. I just kind of assume that if there's a different set of variables in the function,
different function.
potentially different function. Because otherwise it's going to get a little bit messy with the notation.
Thanks.
Okay. All right, so let's look at another example. Here's a Markov network, which has got this sort of representation given by this, some peak, ABC, some peak of BCD. It's a product of these two, and maybe there's some overall normalizing as well. Sometimes we can absorb that if we like. It's one of the touch functions, but it's sometimes useful for this purpose here not to do that. On the right is the corresponding clique graph. Okay, so again, it's very easy in the sense that you just look at these sets of variables here. What are the neighboring variables in common, and then you just put that in separate. Okay, so in this particular case here, we could put into the separator phi BC actually the normalization constant Z. That's one view. It's kind of so we can do that. Maybe it's conceptually useful. And then the cliques have these potentials themselves. Okay, now this is going to what I want to do actually is show you how to represent the distribution as in terms of its marginals, or some of its marginals. So if you remember last week we had an exercise which was to represent this pentagram, this Markov network, in terms of its marginals. I don't know if you remember that. And I sort of got halfway through it and then ran out of time. But sort of what I was attempting to do was to transform the quantities into its marginal representation. So hopefully I'm sure you have plenty of time to go over that and convince yourself that the derivation was correct. But I'm going to do a simpler one here, all right? So, and you'll see hopefully where this is going to lead to in a bit. Okay, so just bear with me for the next few minutes. So we're going to start with this thing, this Markov network. And what I'm going to try to do is to get to this point down here and end up with representing this Markov network in terms of its marginals only. Now this is going to work only for that particular Markov network. This formula is not generally true. We're going to use the properties of this particular structure to get this representation. Okay, so here's one way to do it. We could say put Z over onto here and then sum over D. I'm going to get this quantity. Okay, sum over D. Similarly, you can sum over, say, A, and we get this quantity. We multiply these two together. So Z squared PABC, PBCD is equal to the thing on the right. Okay, and now we can magically combine this phi with that phi. Okay, so we're going to have then this is going to be related to P by Z times by P. So we get Z times by P there. And this one on the right here is again Z times by P, but summed over A and D. Okay, so that's how we get this expression. But so what that means is, if we write this is just the marginal of B and C. So that means, just cancelling the Z's, we get that PABCD is equal to the marginal of PABC, PBCD over PCB. Okay. So it's kind of good to go through this derivations just to convince yourself that it's possible to retransform the distribution into its marginal representation. Okay, so what's interesting about this is if this starts to look like a clique graph, right? In the sense that you could represent this now as some function of ABC, BCD, and look what happens. If you do that, you've got the separator occurring in the denominator. So you have ABC, BCD, BC. So this is kind of interesting because we started out, so our original distribution at the top was a clique graph like this, right? And what we've done is we've showed that actually in the first stage, what were these cliques? Now this one contained phi of ABC, this one contained phi of BCD, and this one contains Z. Those are the assignments of the clique potentials at the beginning. What we showed is through some manipulations, actually, we can use the same clique graph to represent the distribution. But all that's happened is that these potentials have changed now to P of B ABC. This is P of BCD. And this is P of BC. Okay, so these manipulations have left the clique graph invariant. They don't change the clique graph. So, but it's interesting that there exists a set of manipulations which will effectively transform your original clique potentials to some new clique potentials. Where these clique potentials are actually the marginals of the variables in the clique. And if you could do that, that's great, because that means if we want to do marginal inference, if we want to figure out what is the marginal of a variable for this distribution, well, they're there. They're in the cliques, right? They're in the separator and the two cliques. Those are the marginal values. Distributions are there. So what I've just demonstrated is that there exists, at least for this distribution, a sequence of operations starting from our original clique assignments, which would actually give us the answer. Okay. The clique graph form. So this is just spelling that. So I did that by hand, and what I want to do is to find an algorithm which will do that automatically. Okay, that's what the junction tree algorithm will do. It will transform an original setting of and separator assignments to the form that the cliques and separators will contain the marginals. That's the algorithm. And it will do it not in a dissimilar way to what I did algebraically, by a sequence of local transformations. Now, this is where we go do some a little bit what looks a bit complicated, but it's actually really, really simple. Let's define this thing, okay? And then we'll just bear with me. You'll see how this thing works. Okay, so let's imagine that we start out with some simple clique graph. Okay, just two cliques with the corresponding separators. So again, remember that V is now a set of variables, W is a set of variables, and S will be the intersection of these two sets of variables. So this is given, then this is our probability distribution here. And we want to find some new distribution with, say, hats on these things, as their transform objects, which still represents the original distribution. And we want actually these new cliques, ideally again, to be just the marginal settings. That's what we have. So let's figure this out. Let's say that what is P of W? Well, it's a sum over the whole distribution in X of all of the variables in which are not not in S. Sorry, not in what's this? Not in let me just get this right.
Not in W?
Not in W. Not in
Oh, yeah,
No,
that's,
no, it's
it's
correct.
the same.
actually,
Yes,
it's
okay.
correct. So, you remember that basically V contains some of the variables that W contains, because that they are neighbors. Maybe it's a bit easy sometimes to think about, an explicit example like A and B, and say B and B and C, something like this. So this might be B set. This might be the W set. This might be the S set. So we want to figure out what is P of V, because it's a P bit. Well, it's a sum over the whole thing, P A B C, over C, right? Which is basically this set here without a separator. So good. So we just plug in now what is the form of the distribution. That's our Markov oblique structure. W actually doesn't depend upon this variable, it's a constant. So let's do it maybe for this thing here. So this would be, simplify AB, simplify BC, C, B. I'm going to sum that over C. This is phi of AB, sum over C, and phi of BC over IB. Okay, so that's what I'm writing down here. Okay, so complicated notation for the same thing. So in some sense, what we're doing now is we're interested in the marginal PA. So what we're kind of doing, sort of the way to think about this is we're kind of summing over C. So we're kind of passing information from this clique towards this one. This is the kind of conceptual idea, a little bit like a message passing. So the idea is, when we pass that information from this clique to this one, we need to sum over the variables which are in this clique and not in this one, namely C. Because you need still the B function dependence. So we just sum over C. Okay, so this is the idea. This is called absorption. So we're going to absorb the information from this clique passing through this separator to this clique. This is the conceptual picture. Okay, so just by symmetry, I have a corresponding expression for the margin on this clique. I could go this way and sum over B, summing over A, to get the information passed to that. So these are true statements in general. So one notation you could say is, well, this cluster or this clique W, that absorbs information from its neighboring clique B. So one way to do it is to, just to define these operations here. What is this? Well, one way to just represent this thing here is that we could call this thing a new separator. So I'll call this thing, in general, the new separator phi star will be defined to be given by this. And then we find that the new potential would be simply given by this. So in other words, let's imagine you going, say, from V, I've written the actual potential here down as well. So from phi of V, this V, to this one here. Right, we're going to absorb from V to W through this separator. Well, that means we're going to sum this guy over everything which is in V, which is not in W. So it's basically given by this. And this defines the new potential, which is the original one, times by the new separator divided by the original separator. So this is what we're doing here. So the new separator here divided by the old separator. This is a function on the separator. Okay, so that's there's only two things that you need to remember. PV. This is the, so when we go this way here, from here to here, you find a new separator, phi star, which is basically the sum over this one for everything which is not an S. Okay, and then the new potential here is just the whatever we had before, phi W, times by the new separator divided by the original separator, and that's the transformation. So what I'm going to try to, I hope will not fail to do, is to find you that this transformation is the right thing to do in two senses. One of them, that we will leave the distribution unchanged, in the sense that the cleat graph here, the product of this divided by this, is still the original distribution. Okay. And furthermore, that when I've done this, this guy here will contain the marginal of B of V. That's already, you already know that actually, because that was given by here. The marginal P of V is given by the original potential times by the new separator divided by the original separator. So that's already there. But let's look at the invariance then. Okay? So what is the product of the thing? So we've got the original phi here. We've got the new phi divided by the new separator. Right? So if we get this right, we've got our phi of V. The new separator was the original separator, that's the original potential, times by the new separator divided by the old separator, divided by the new separator. So these new separators cancel out, and we're left with the original distribution. So that's kind of nice, right? So yeah, I just repeat myself. Maybe sometimes it helps. So so what have we done? We showed that this transformation of these potentials, this new star potentials, does not change the distribution, in the sense that if I were to take the cleat graph, take the product of the new separator potentials divided by the product of the new separators, it's still exactly the same distribution. Nothing has changed. Okay. What I've also showed is that, at least in this representation here, that phi star of W contains the marginal P of W. So we're getting there. This is close to what we want, right? We want these marginals to contain these cleats to contain the marginals. So that's good. Yeah. So this is what I'm going to try to show you here. Actually, is a little bit more complicated, but it's the same idea. So what I want to do now, so I've gone this way from here to here. Okay, so what I'm going to do now is I'm going to go back from here this way. Right, so if I start out with, really this thing is kind of obvious, that actually I already showed that if I go from V through S to W, that I will end up with a marginal P of W on the right hand side. So by symmetry, because these phi's are anything that you like, I can go back from W now through the new S back to V. And again, V will now contain the marginal PV, just purely by symmetry arguments. Okay? So when you've done that, what it will mean is that W will contain the marginal P of W, and V will contain the marginal V. And it has to be that S is the marginal on S. So if you like, you can, we can attempt to show that. So maybe let's see how we get on with this thing. So just to spell this out again. So we're starting from here. We're starting from V. I'm going to write the potentials down, because otherwise we will maybe get a little bit confused. So this is our original cleat graph. Stage one was we went from here, absorbed through to here to get to there. And that meant we ended up with phi of V. We ended up with a new separator phi star S. We added a new potential phi star of W. We're now going to go, this is absorbing this way, we're going to absorb back this way on this graph. Okay, so what will happen is that we won't change phi star of W, but we will change this separated potential here. We'll define a new one. So let's say call that, say, phi star star. Okay. And we will change this one here. So depends what phi star. Okay, so then we will have absorbed through the separator in both directions. And what I'm attempting to show you here algebraically is that in doing that, this new potential here, phi star of V, is the marginal P. Okay. And the new potential phi star S is the marginal P-less. I don't know how profitable it is to go through this tortuous derivation. It probably will confuse others potentially more than rather than help. I mean, these are things that perhaps are a little bit easier to just see on paper than, but it's a sequence of basic operations which has to be sorted. And but you get the idea. I think it's intuitive that we showed that this. It's clear, where this definition of absorption comes from. It comes from the requirement that if we start with the original distribution, we just sum over a quantity. This then defines the message, the absorption message. It's clear that that's going to give rise to it. Okay, so that's good. So then, how do we generalize this to bigger structures? So let's imagine now we have a more complex looking, say, a tree of cliques. Okay. It's a clique graph, it's a tree, it's a single connected clique graph. So again, remember that these are all sets of variables, and it's not a Markov network. Okay. It's not a factor graph. So what we want to do is we, absolutely analogously as to before, if we've got this clique graph, it's going to have an edge, or at least one edge somewhere. It's two edges. There's going to be an end, like say here, C. Right? So what we could do is, in the end, we want to, when we do the absorption, it corresponds to carrying out a summation over all the variables in here, right, which are not in this separator. So we want to basically, pass information from here to here. So we need to sum over the variables in here which are not in here. Which is the separator. Well, which is this minus the separator. Right? So we could start from here, right? So we could sum over those variables, defining a new separator here, and then updating whatever we had there, right? Multiplying the original potential by the new separator divided by whatever the separator was there. Okay. So that's one place we could start. When we've done that message, we can then continue. We say go from here to this one. Right. We could then say, well, we can't go from here now to here because I haven't yet collected all the information from the other nodes coming into this node here. So what I'm trying to impress upon is that we need this guy, he needs to know his marginal information from all of his neighboring nodes before he can sort of say, well, I know kind of where I am in P of D, I need then to just pass that information towards this node here. So there's a schedule here of operations very similar to what you would do in the factor graph representation or something similar to belief propagation. So you can only pass a message once you receive all the messages from the neighboring nodes, or all the required messages from the neighboring nodes. Okay, so again, we can go from this one to here. We can go from here to here, but then we have to wait. We cannot go further. We could do, though, for example, this one from here to here, that's okay. We could do this one, say, from here to here. And now, we could do this one from here to here because we've got all the incoming messages. This one, and this one, to pass from here to here. So the general structure is you say, if I want to pass a message from, say, here to here, right? What do? I look at the neighbours of this node, and I ask myself, apart from this neighbour, which I'm trying to pass a message to that neighbour, have I got all the incoming messages from the other neighbours? And if you have, you're good to go. You pass that message. Otherwise, you have to update. You have to form another message, a different one. So there are many, in general, okay schedules, right, for a given graph. Here, you could have started from here to here. You could have done that one, you could have done that one, and this one, and this one, There are many, many different schedules, but once you've passed a message, all messages, both ways across the separator, all separators, then you're done. Nothing will ever update anymore, and the algorithm is finished. So let's just spell that out. So go from here to here, right? Then you go from here to here. In this case, we're waiting that we go from here to here. Then do from here to here. Then we 4, 5. Yeah, okay. Go from here to here. That's okay. Looks like I've decided now to go from here to here. And to broadcast out this way, and then I go back this way. I mean, it's really, there are many, many different schedules we could have done that, which would have been all okay. Yeah. So the claim, which I'm not going to formally prove this. There's a more formal description in one of the exercises or something at least in the online version of the book, which sort of tries to explain why this is kind of obviously correct. Why it's correct. Okay. So this is nice. So it's another message passing algorithm like we had in, say, factor graph representation, right? We've got the same concept of the message scheduling in the factor graph representation. Maybe I didn't spell it out enough there, but it's exactly the same. To pass a message, you have to wait until you've got the messages from the incoming neighbors. It's exactly the same idea. It's just the difference is that the message itself has changed. Okay, so we're going to plow on and see how this works now for a particular example. So we're going to take a markup network. We're going to compile it, if you will, into a junction tree, or a peak graph, I should say. And it's going to form a peak tree from this peak graph, and then we would pass these messages to absorption on the peak tree. So this starts with this markup network. So that means it's got it's a product of cliques on 1, 4. 3, 4, and 2, 4. I want now to represent this as a clique graph. So I've got a clique on 1, 4, I've got a clique on 2, 4, and I've got a clique on 3, 4 with corresponding separators. Now, the frustrating thing is it's not a tree. You've got this cycle, this loop in here, which I don't like very much, because if I've got that, I don't know where to start this message passing algorithm. There's no edge on this graph, right? So it doesn't seem to be useful. So when I'm, again, with some complicated algebra, not really some messy algebra, I'm going to try to persuade you that actually you can drop any one of these separators here. You can break this cycle with no loss of generality. So let's just go through it. So again, there's a lot of bear with me today, but hopefully at the end of the day we'll all coalesce into one beautiful picture. Right. So let's our original distribution. So we're going to do some things. I'm going to play the same trick as before. We're going to attempt to represent this distribution in terms of its marginal quantities, like we did with the other graph. So, for example, I can say, well, Px1, x4 is the sum of x1, x3 is this thing, and I write it down. Similarly, x2, x4 is given by this expression here, and x3, x4 is given by that expression. And now that's nice. I try to then re-represent the distribution. So I take the product of these three, and this is a big factor here, and then I get, if you look at all these things down here, you'll see that I get basically this term here, for example, that also occurs down here twice. This term here occurs twice down there, and this term occurs twice. So actually what's happening is I get essentially the sum of this one, and this one twice squared. Okay. But actually, if we again just collect these sums at the front, of course, this is just the sum of the original distribution over x1, x2, x3. So that's just the margin of x4 squared. So what that means is that the original distribution can be written as in the form the product of these three marginals divided by the product of these two marginals. So that means that we could represent this as a clique graph, and if we did that, we'd have, say, x1, x4, but now we're going to have two separators. We don't need three separators. See? So in fact, this clique representation here is redundant in some sense, so we don't need one of these separators. We can drop it. So there's a general result, which again I will not prove, which says that if the original markup network were singly connected, you can go through some sequence of operations like I did there, such that the representation, the clique graph representation, or there exists a singly connected clique graph representation. In other words, if you naively started with your clique graph and you had a cycle there, a loop, which rendered that not connected, you can remove a variable in that loop. If it appears in the loop on every point, you can remove that variable in order to render it singly connected at some point. It's up to you where you decide to remove it. It doesn't matter. Okay. In other words, I could have put the link in here and drop that one and that one. Three different graphs. Okay. Good. So now, basically, when we've done this, we end up with a clique tree. Alright, so this is nice because what it means is that if I start out with a singly connected markup network, I can compile this into a singly connected clique tree. Now, so there were a lot of different terminologies, and I don't really know why they call this the junction tree, but I just prefer myself to call it the clique tree. But anyway, it's kind of, yeah, it's also common to call this thing a junction tree. But let's look at an example. This is a clique tree here over various sets of variables. So to be honest, I don't really know why they have this different word for this thing. I think it just comes from the fact that originally the mathematicians were called as a clique tree, and then the statisticians they called it a junction tree. But it's really the same thing. Maybe there's some minor implementational difference. It's really the same concept. But the point is that one property that this clique tree will have is the following thing called the running intersection property. So what this means is that if you've got this object, if everything is worked out well, so we will have the following thing, that if you find a clique which has got two cliques which share a common variable, let's say this one here, they both share the variable e. Okay? So what will happen is that e will appear on the path between these two cliques, both in all cliques and separators on that path. In other words, here, E is the common variable, and it appears in the separator and the clique on the path. Okay, there's kind of intersection property which is running along the path. Running intersection property. Let's check it out. So we could just verify it, simply for here. We've got, we can start with A. Well, A only appears here, so that's okay. B only appears here, so that's okay. What about C? If C appears here, if that's a running intersection is satisfied, here and here, that's clearly okay. D is only here, that's okay. E is just here and here, and F is just there, so that's okay. So if we've got a valid, I guess maybe the distinction really is that you could write down a clique tree and sort of say, well, it's just a tree of cliques in some general mathematical sense. But in this probabilistic framework, if we've done these things correctly, transforming in some original Markov network in this form, we will end up with this additional property that these cliques satisfy this running intersection. Maybe that's the distinction in some sense. Okay, and what the meaning of this, in some sense, is that because of this running intersection property, when we do this message passing, in some sense the marginal information is kind of being propagated across the whole of the graph. So this means that this local consistency, so when I sort of, I said, well, if I go from here and I pass to here, I know that this guy will now contain a margin P of W. If I were then to propagate further to a neighboring clique, that marginal correctness will propagate to the next guy. So that whole thing will, if it's all connected correctly, will propagate to the rest of the graph. So the whole thing, from being locally consistent, will become globally consistent. And we'll end up with all of the cliques containing the marginals of the distribution. So that's why you need, in some sense, this running intersection property. It will just hold, provided that we start out with a singly connected structure. You will end up, if you've done it correctly, you will end up with this running intersection property. It will always be like that. This running intersection property is useful to prove that when we do this local absorption, that the whole distribution, at the end of going both ways across separators, that we will end up with the marginals of each of these. So let's look at another example. Let's imagine we start out with this belief network, and we want to then, we want to compute marginals for this belief. So P of whatever it is, E. So what do? We talked about how to compile a Markov network into a clique graph, but we know how to compile a belief network into a Markov network. So we need to do that initial stage first, and then we'll compile that Markov network into a clique graph. Okay. So let's start with this one here, belief network, and represent this as a Markov network. So don't worry about the fact that we will lose some independence properties, or we will not be able to then look at this. It may not be a perfect map anymore, but it doesn't matter, because numerically that's then we just check this in the computer such that this numerical transformation is correct. Okay, so start out with this. It has to have that Markov network representation. Why is that? Well, let's look at this variable here. C has got A and B as parents. So there's a sort of a P of C given AB. So as a clique, there has to be an ABC clique. So in other words, wherever you see a variable with parents, all the variable and all of its parents have to get compiled into a single clique. In this case, it's an ABC 3 clique. So we have to, unless we could do that, with this, we could compile this into a 3 clique. These are just 2 cliques, and these are 2 cliques. But this then is a Markov representation. We could numerically represent this belief network in this Markov network. Like I said, don't worry about the fact that you cannot maybe interpret all of the independencies here. Just the numerical compilation would be correct. So you get the usual jokes. So this is called moralizations property. Okay, so what you're doing is you're marrying together unmarried products. so forth, making a moral graph. Come up with parents that are not married. It's immoral. Okay, so now what we do is we compile this markup network into a clique graph. So what are the cliques here? We've got a clique ABC, clique DCE, clique CF, EF, GE. Those are those cliques, ABC, DCE, CF, EG. I now have to link these cliques together according to the Markov property we have. So for example, I know that ABC is next to DCE, and they share the separator C. ABC, DCE, they share the separator C. Similarly, I know that ABC is neighboring CF, sharing C, etc. And I keep going like this. So I write down all the cliques and all the neighbors of these cliques, and I draw a separator. I get this clique graph. My next step is to transform this to a clique tree, which will turn out actually in fact to be a junction tree. Okay, so as before, we had now cycles here, but as I was trying to sort of suggest before, we can drop any of these connections because this variable appears everywhere in the cycle. So we can arbitrarily drop, say, this one and say this one to make a clique tree. So my claim is now that this thing here is a valid clique graph representation of the original belief. In other words, there exists an assignment of all of these clique potentials and separated potentials which would represent the original belief. So, more generally, to transform from this clique graph to this clique tree, then one way to do it is to say, well, look, you could basically find a spanning tree of this graph. What do I mean by spanning tree? I mean, you have your graph, and you find a tree which spans all of the nodes in that graph. So in other words, let's say you have 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a graph, but it's not a tree. It's not. So when I say tree, I mean a singly connected structure. This is not a tree. It's multiply connected. A spanning tree is a tree which goes through all of the nodes of this graph. So there are many. So one would be, we could do this, do this, we could do that, we could do that. Right, so we've gone through all the nodes, and it's a tree. And there are many other spanning trees. So what you could do is you could say, you could take your clique graph when you do this compilation, okay, and then you'd find a spanning tree for this, where actually what we also do sometimes in more complicated situations, maybe you might have more than one variable in this edge. So maybe you might have a kind of a weight. So let's say that the weight of these edges here corresponds to the number of variables in the separator. So you might have one variable here, you might have two variables here, you might have three variables there, one variable, two. So every edge in this graph here will have, so the graph nodes are represented by the cliques, and the weights of these edges are represented by the number of variables in the separator. Okay? But then, of all the possible spanning graphs that exist, I find that one which has got the biggest weight. In other words, the sum of the edges in the spanning tree, whatever it is. There's no other tree which would have a larger summed set of weights. Okay, that's the maximum weight spanning tree. So typically the simplest thing that we do is we find the maximum weight spanning tree for this, and then we just use that spanning tree as the actual graph structure, the clique graph, the clique tree. Okay. So there are, in this case here, there's more than one maximum weight spanning tree. There are 6 as well. Okay. But in general, there may be others. But this is, you don't have to do this, but it's useful to do that. It's helpful to do that. Okay, so that's the process. So now we've compiled our belief network to this junction tree. So we're kind of, almost good to go in the sense we can start passing messages on this junction tree. But we just need to assign the potentials first. Obviously, we need to know what these values are in this big tree, this junction tree. Okay, so we need to do that. So what do we do? Well, we started out in our belief network. We've got this P of A, P of B, P C given AD. We've got this list of 1, 2, 3, 4, 5, 6, 7, 8 factors that are, in this case, conditional probabilities. We need then to take each of these probabilities and we need to drop them into at least one of these clique on the clique graph. Okay, so let's look at the potential, say, P of C given AB. That's got to be dropped somewhere on this clique graph. Where can it go? Which clique could accept P of C given AB? Well, there's only one. Because there's only one clique which contains A, B, and C. That's got to go into the ABC clique. What about P of A? Well, again, there's only one place where A occurs. So that's got to get dropped into the ABC clique, etc. Right? So I don't know in this case, maybe you need actually assignment, but sometimes there may be more than one possibility. So we could drop these potentials into the various cliques, and if we set all the separated potentials to 1 initially, then we're good, right? Because obviously then if we take the product of all these clique potentials, this one, this one, this one, this one, and this one, we've got the original distribution, the belief network, and we divide by the product of all the separated potentials. They're all 1 to start with, so we've got actually the original belief network. Okay, so just to restate that, what we've done is we've translated this belief network into this clique structure, and we've assigned these potentials such that the product of these potentials is exactly the same as the original belief network. So we've got a correct representation of the original distribution in terms of the clique tree. So that's good. Now, you can start to do message passing on this clique tree, this junction tree. Yeah? So, for example, you can start from here and pass up to DCE. So, why don't you tell me? Somebody give me, somebody shout out a valid schedule. Where could we start? I'll give you a start. Let's get from here to here. Okay, so go from there to there. Yeah. What else what's the valid next step we could do from here to here? I like the right side forward actually, that's number 1. Somebody tell me where number 2 can go. EH to BC. EH to BC. Yes, good. another one.
BC to ABC.
DCE to ABC. Oh gosh. That one. Yeah, so that's say number 3. And then
CS to ABC.
C, that's true.
Pull it down. Let's put it out so it's back away.
And then what? Okay, so that's 4. And then what?
ABC to DC. ABC to CS.
ABC to DCE, yeah, that's good. And we can do 5. And then I guess we can go back this way, right? We can go from here to here. That would be 6, and we can go from that. Yeah.
Plus ABC down
ABC to
CS.
C.
Oh, sorry.
ABC to CS.
Oh, we have got this one already.
No, the other.
No,
Yeah,
the
no,
right
to
hand
CS.
branch.
ABC to CF.
Right.
Yes.
The reverse of 4.
8. Okay, so then we've got, if we've done it right, we've got arrows in both directions on all separators. So then the claim is, when we've done that, what we'll be able to do is say that, we'll just look in the computer at whatever is stored in the table for the new phi, at the end of this procedure on EG, and it will be numerically equal to the marginal P EG. So let's say, somebody says, well, actually I want to know what the marginal E is. Well, that's okay, because we know what P and E comma G is now. So to get the marginal for E, that's easy. We just sum over the states of variable G. So if you want to know, what is the margin of a variable within a clique, that's okay. You just have to sum that margin in that clique over whatever variables are required. If you ask me a more complicated question, like, yeah, but I wanted the marginal P of E comma F, how do I do that? Because they're not in neighboring cliques, and I will say it's harder. It's much harder. But at least for this case, margins within a clique, it's easy. So okay, I just want to say that I don't know if you get the idea now. I mean, this may seem all kind of rather pointless, given that we already have algorithms like factor graphs, etc. Right? What will turn out to be useful is that this algorithm will generalize to the case when the structures are not singly connected. It's not possible to do that with the factor graph representation. So this is where the beauty will come in. The other thing to say before we move on is that, again, this is the margin inference. So what would happen is that if you want to compute the most likely state, say the map state, all you need to do is just redefine the absorption operation. So wherever we had sums, they just get replaced by maxes. That's all you'd have to do. Or whatever more general algebraic operation that you would like to do. Okay, so that's the generalization to computing the most likely state. It's just exactly the same, just with a change of operator. You have a choice. You can have a break now, or we can start talking about this one. Do you want to have a break now? I think it's maybe a bit much stuff. So let's come back at 12:30.
I need to get rid of that immediately. It's completely lost track. Completely just started daydreaming.
It's really embarrassing again. You've got to the point where I've lost track of what you were doing the derivation on the board. So sorry, it was absolutely trivial. It's like, yeah, okay, yeah, that was obvious.
Just could not keep it out.
give you a little time here around. Always happens. I've got stuff to inside now.
Can you stand up?
Jennifer's playing the ball. I can pass it. I'm going to get another one.
Oh, you're still up. Perfect. Not bad, it's not. Have you finished this one? Are you working with anyone? That is a lot of work on your own.
No, I mean,
17.
just so you can you do a one?
I know 17 is right, so a few people have said 17 I was working with. Oh yeah. Yeah, it's quite it does depend how you define it though. Yeah, there could be 15, there could be 17, there could be 19, depending on what you count as a maximum of work. Most people are 64.
Just sending, not connecting.
But I can send that one.
Have you?
For a file like that.
Oh, okay.
All the messages you know what he's talking
That's
about.
true.
How can you just send them even though it's
Because it has to go in some way, right? You can't just
I think it's one of those
otherwise
courses.
no one moves.
If you read the book before the exam, you'll probably do fine.
Yeah, I see. But how we can't write this point.
Oh, is it difficult?
Oh, I see. Because
There's a lot,
you
isn't
have
there?
this
There's quite a lot to
here.
remember.
Yes.
Yeah.
Yeah, I see.
Yeah. What's the point? Yeah, because I'm just going to
It's quite long.
It's quite long.
Well, it depends. If you run his run the map script, simply okay. You need to do it by hand.
Obviously, you have to know that variable.
Well, I've used Excel, but
The structure that you can exploit to make that sense.
You mean numeric structure as in, because these are all zeros and ones that some sums go away. In that way, yes, but symbolically, no. Not less than. So you see a sum with 4 variables, that's what I'm interested in. Okay.
Right.
It can become less than that.
For the big ones.
I see.
You see 4 here, right? PUD.
Yes.
I understand how this works.
But there is structure which enables one to reduce this.
I have a question.
Something like easier.
I'm perhaps I'm missing
I think maybe you're missing
just one more, yes.
Yeah.
Yes.
You have a question?
Oh, this is, yeah.
If two neighbours are the same, it's set to 10. If they're not, then it's set to 0. And the second part of it is the bit that was basically written like this.
Yeah.
Is that so? This is equal to 2 if pixel in is equal, but this particular bit here is equal to 2 if the pixel, the clean image, and the dirty noisy image are the same. Is that correct? Is that what it's supposed to be?
Yeah.
That's how what I understood it to be, but it looks as though it should be equal to 2 if they're both equal to 1. So equal to 0 if they're both equal to 0. For example, if
this is from the code, right?
Exactly, it's from the assignment.
Video running.
That's probably a typo. Yeah, it's a typo.
It's a
So-
typo. Okay, cool. Okay.
Just let me check this.
Okay.
What time Brooks, second member.